So in this lesson, we're going to be talking about differentiability. And remember, if you can differentiate something, it means that you can take the derivative. So differentiability is basically the ability to take a derivative, whether you can or can't, whether it exists or it doesn't. So this first whole category, we're going to be talking about situations in which the derivative might fail to exist at a certain point. So now notice it says f prime of a, so that represents a specific value of x. It's not really possible that the derivative wouldn't exist at all. It's definitely possible that it couldn't exist at a certain point. So this first sentence here says function 1 of a derivative at a certain point where the slopes of the secant lines, remember, our secant line here. So f of x plus h minus f of x. Remember, x is whatever point you're talking about. I guess actually, I'm sorry, this should probably be an a, since we're talking about the point P of A. So as x approaches A, we could also, this makes more sense to say as h approaches 0, since that's the way we've been talking about it. So, sorry, a couple quick little errors there. So f of A plus h minus f of A over h fail to approach a limit as h approaches 0. So one of the things that we always talked about with limits is that you need to make sure that the left-hand limit is equal to the right-hand limit. So this represents a slope. So basically what you're trying to figure out is whether the right-hand slope is the same as the left-hand slope. As you're coming in from the left-hand side, does the slope from the left appear to be the same as the slope from the right? And we saw a couple of examples like that in the last couple sections, but we've got 4 different ways, 4 different kind of features on a graph that could end up meaning that the derivative doesn't exist. So the first thing to keep in mind is that a graph needs to be smooth. So it can still be continuous but not be smooth. And so we've got 4 examples down here where this could occur. So first thing is something that we call a corner. A corner. All right, so let me draw an example on here. So a great example of a corner would be the absolute value function. So the reason that the limit doesn't, or the derivative doesn't exist, and it's just at this point right here at x equals 0, this is because the one-sided derivatives differ. If you're looking at an absolute value function, as you come in from the left, the slope is a constant -1. As you come in from the right, the slope is a constant 1. So the left-hand limit is -1, the right-hand limit is +1. The one-sided derivatives are different, and so that ends up being a corner. We've got something relatively similar called a cusp. So like I said, pretty similar to a corner. It looks something like this. So like I said, pretty similar. It's not all that different from a corner. You can see it's not smooth at this point. Again, these are all going to be at x equals 0 that we're talking about. What a cusp does is that the one-sided derivatives approach infinity and negative infinity. So as we come in from the left, the derivative is actually approaching negative infinity. It's getting more and more steep in a negative way. And then as you approach from the right, this is approaching positive infinity. Again, getting more and more steep. So definitely a slight difference between the corner and the cusp, but either one of those, if you see it, you know the derivative doesn't exist at x equals 0 here. The derivative doesn't exist at x equals 0 here. The third one is a vertical tangent line. If you would have a vertical tangent line to a graph, then that means that the derivative doesn't exist. And so this is a good example here, something like this. So it looks something like that, again, right at x equals 0, because that's the point that we're talking about. Right at x equals 0, the tangent line that you draw would be vertical. And this graph is something, like the cube root of x, something like that. And if you were to take the derivative of the cube root of x, work everything out, you would end up with something that would be undefined if you tried to plug in x equals 0. So here, the one-sided derivatives are both either positive infinity or negative infinity. So here, as we approach from the left, our derivative looks an awful lot like positive infinity. Here, as we approach from the right, our derivative also looks a lot like positive infinity, so it's almost like flipping one of these pieces right here. But even if they both approach the same thing, your derivative, your slope, can't be infinity. Having an infinite slope means you've got an undefined, a vertical slope. So that would be a point where the derivative doesn't exist. And then the last one would be any sort of discontinuity. If there's a discontinuity at all, then the derivative wouldn't exist either. So something like this, just a nice simple graph. So this would mean that one or both of the one-sided derivatives does not exist. So as you come in from the left-hand side here, the derivative doesn't exist at this one point, and that's because of the hole in the graph. So even though as you approach from the left and as you approach from the right, it looks like the derivatives are both zero, we've got this issue with discontinuity right here, which means the derivative can't possibly exist at that point. All right, so example 1, we want to find all points in the domain of this absolute value function where f is not differentiable. So this is something, we're not going to use our calculators for this. We should know what this absolute value function looks like. So we know that the normal absolute value curve is like that v, just like we have right here. And then we've talked about transformations, like what these two numbers do in here. So the x minus 2, that means it moves 2 units to the right. And then the plus 3 means it moves 3 units up. So instead of having that little peak right at 0, 0, the peak for this one is actually going to be at 2, 3. So we move 2 units to the left, to the right, and we move 3 units up. So our absolute value curve is going to be centered right there, something like that. So what we notice, and this is just like the corner that we had up in example number 1, as we're on the left-hand side here, everything on the left-hand side has a slope of -1. And then everything on the right-hand side here has a slope of +1. So this is one of the corners that we had up above. As we approach from the left-hand side and as we approach from the right-hand side, the two slopes, or the two derivatives, are different. And so as we get to 2, which is our issue right here, when x equals 2, the left and the right-hand derivatives don't match up, and so therefore the derivative doesn't exist. So we would say that this function is not differentiable at x equals 2. So now, like I said, it's extremely rare that you would say that an entire function isn't differentiable, and there are weird examples like that in math, nothing that we're going to see. But for this one, you'd say that it's not differentiable at a specific point. Same thing with continuity. Most functions are continuous at least somewhere, but they have points of discontinuity. Same thing. These have points where they're not differentiable. But anywhere else, I mean, it's differentiable anywhere to the left of 2, it's differentiable anywhere to the right of 2. Okay, so this is kind of what I was just talking about. So most of the things, most of our normal functions that we come across, they're differentiable all the time. It's pretty rare that we see something that has that cusp or that corner or vertical tangent line or a break in the graph or something like that. So anything that looks smooth, unbroken, and then it says with a well-defined slope at each point. Well-defined means that it's not infinity, not a vertical tangent line. So here are some differentiable functions. So first category, I'm just going to give you all of the different categories of functions that are always differentiable. So polynomials, always differentiable. You'll never see a corner or a cusp, anything like that in a polynomial. They're just smooth and continuous. Rational functions. So even though there's points where there might not be continuity, there are points everywhere where it is continuous, those graphs are perfectly smooth. Trig functions. Sine and cosine, always smooth and continuous, and then you've got your tangent, cotangent, secant, cosecant, where again, everywhere where they're defined, they're smooth and differentiable. Exponential, no problems with differentiability. These are just smooth and continuous. Same thing with logarithmic functions. So notice a couple of them that are not in here. Absolute value will usually have some sort of issues. Radical functions will usually have some sort of issues. And yeah, anything that's piecewise defined could definitely end up having a break, which would result in that fourth scenario that we saw in the front. Number 2, kind of a different category here. Composites of differentiable functions are also continuous. Are also differentiable. So composites of differentiable functions. So remember, composition means to plug one function into another. So if you plugged, let's say, a trig function into a polynomial, or if you plugged a exponential function into a trig function, like sine of e to the x, something like that, because they're both differentiable, the composition of those two functions will also be differentiable. And third, sums, differences, products, quotients, and integer powers. So only a function raised to the second, the third, whatever. It can't be raised to a fraction power because that would be a radical. And of course we add in this little note that says where defined. So of course this, we could definitely come up with some issues with quotients. If you take the quotient of a differentiable function, you could definitely end up with a denominator that's going to be 0 somewhere. So as long as it's defined, it's going to be differentiable on that entire area. All right, differentiability implies local linearity. So local linearity basically means, if you think of what the word linear means, it's a line. Any linear function is a line. And so linearity is basically taking on the behavior of a line. Locally means just on a very small little zoomed in area of the graph. So this is a good way to think of differentiable functions, that they are locally linear. So what this means is that a function that is differentiable at a closely resembles its own tangent line. Let's say very close to a. So a, remember, is an x value. That's where I'm trying to find the derivative. So this definition is going to feel a little bit weird until we look at the examples down below. And we've talked about this kind of in class, and I was walking around talking to some of you guys. If you zoom in on a function, the closer you zoom, the more you can see the slope that we're supposed to be taking on at the tangent line. The closer you zoom, the more the curve kind of starts to look like a straight line. And it's just around one particular point. So both of these, example 1 asks if either one of these functions is differentiable at x equals 0. So what we're going to do is we're going to graph the functions, and then we're going to zoom in on x equals 0. So I'm going to add a graph page here. So I'm going to graph this first one, absolute value of x, which if you are Inspire people, the absolute value key, you have to hit this weird button next to the 9, and then one of your options, the one right here, is the absolute value. So we take the absolute value of x, and then outside the absolute value do +1. So we know what this is going to look like, hopefully. It's just a normal absolute value curve shifted up 1 unit. So our graph looks like this. So we should know, just going into this, this falls under the category of corner that we saw on the front page, and so we should know that it's not differentiable, but I want to show you exactly what happens as we zoom in on the point x equals 0. So again, hit menu, and then there is a window zoom option, and you can zoom in by hitting number 3. So it's got this little magnifying glass, so you want to zoom in right around that point. So hit enter. So as we zoom in, we're getting closer and closer in here. So now notice we are pretty zoomed in. If you look at the values on the y-axis and the values on the x-axis, we're now like, negative 0.16, positive 0.15. We are zoomed in very, very, very close, and nothing appears to be changing here. Even look at my y-axis. I am like 2/100ths of a unit in both directions, and this still looks exactly like an absolute value curve. It doesn't appear to be flattening out. It doesn't appear to be looking linear, even though I'm super, super zoomed in. Look at both of these scales. So it's not changing anytime soon, which means the left-hand limit definitely is not the same as the right-hand limit. So this is not differentiable at x equals 0. And the reason behind that is that that corner that we were just talking about, it doesn't ever straighten out. And I'm assuming you could tell that no matter how far I zoomed in on that graph, that corner was never going to straighten out. All right, so let's look next at part B, which actually it's a remarkably similar graph. It's got the teeniest little difference here, because if you take the square root of x squared, you get the absolute value of x, and then of course 0.99 is quite close to 1. But if we graph that one, so let's plug in the square root of x squared plus 0.0001. and then outside we've got plus 0.99. So when we graph it, like I said, it's remarkably similar to the absolute value of x plus 1. And so when you're looking at it here in our standard window, looks like it's pretty much the same graph, looks like it comes to a corner, but I want to show you what happens here. So we're going to do the same commands, menu, and then zoom, and we're going to zoom in. So when I click right here, when I'm zooming in on this one particular point that appears to be a corner, still looks like a corner, still looks like a corner. And now that we're getting pretty close, can you see now there's a teeny little dip here where it doesn't look quite so pointed. It looks like it's slightly curved, and it looks like it's slightly curved again. So the farther that we zoom in, and now I'm incredibly zoomed in here if you look at my axes, but can you see it's starting to actually look like a curve and not like the pointed corner that we see in the normal absolute value curve. So now it's spreading out quite a bit. We're very zoomed in here though. Oh, it's now really different from a corner. Zoom in maybe once or twice. So now we're in and in again. One more time, and it almost looks like a line. So I'm incredibly close in on this graph. And now, see, now I've got it to the point where it looks like a line. If you look at those x values, that's a ridiculous, ridiculous zoom. I'm super close up. But when I zoomed way, way, way in on this curve, the corner actually did flatten out. So this is what it means to be locally linear. Locally means kind of around the point x equals 0 that you're looking at, and we of course know what it means to be linear. So the farther we zoom in, it actually does end up straightening out, and so it must be differentiable there. All right, so the graph does straighten out at x equals 0. And so what that means is that it must be differentiable at x equals 0. Okay, so the next thing we're going to do is we're going to talk about how to find derivatives on a calculator. We've spent a couple days doing this derivative thing by hand. Now this is a way, and I'll talk more about this in class. On the AP test, we've talked about how there's a calculator section and there's a non-calculator section. On the calculator section, they're expecting you to find any derivative that you need just by plugging it into your calculator. Like I said, we'll talk about this more. So unfortunately, I don't have the old operating system for either the 83 or the 84 or the 84 plus, but I can show you what the new operating system does. So it starts off the exact same way. What you do is you hit the math key, which is over here on the left-hand side, opens up a menu that looks like this. And so we want to go down just below what we can see, and it's right there. So it says n-deriv, that stands for a numerical derivative, and then it opens up a set of parentheses. So if you've got the old operating system, and you won't know until right about now, so when you hit enter, the new operating system looks exactly like the form for a derivative. That's that like d by dx that we had talked about in class, that separate notation. If you have the old operating system, all that showed up on your screen would be n-deriv. So let's start with the old operating system. You type in the equation. So, you know, let's try out like x squared. So type in x squared and then hit a comma, which the comma is right above the 7. And then comma, then type in the variable x, which is right up here next to the alpha key, and then comma again, and then a is the value that you're trying to find the derivative at. So let's say we want to find the derivative of x squared when x equals 1. So you type in x squared, comma, x, because that's our variable, comma, 1. If you've got the new operating system, you plug everything right in. So we want the derivative with respect to x. So you type that in here, and then you can type in your function, x squared, and then over here, that's when x equals, then we can type in 1. And when you hit enter, it just takes the derivative for you. So this is something, hopefully you remember, we've seen this one before, but the derivative of x squared when x equals 1 comes out to be 2. And our calculator can do it, obviously, in fractions of a second. So that is the 84 plus. We've got the commands right there. The inspire, what you're going to do, we've got a couple of different options here. If you're on just like a normal calculator page, oops, I forgot to do the graph one for the 84 plus. We'll go back there in a second. So from a calculator page, you want to hit menu, and then we've got this whole wonderful menu for calculus. So hit the number 4, and then you can take the derivative at a point. Yours might say numerical derivative at a point. Mine's a slightly different version. So either way, that's the one you want. The variable is x. Either it's already there or you can type it in. The value that we're looking at we said was 1. And we're taking the first derivative. In the future we'll take second derivatives, third derivatives, but that's nothing we need to worry about right now. So hit OK. And the function we're typing in is x squared. So the format looks exactly the same as the way it did on the 84 plus. So go ahead, hit enter, and we get that same value of 2. So say for instance that you're in a graph page. So let's do that. Open up a graph page on the Inspire and graph x squared. So there's our function. We know what it looks like. So at 1 we said supposedly our derivative was 2. So hit menu, and then there's this menu for analyzing the graph. So hit that. And then we've got all of these options here. That's our notation, dy by dx, that represents the derivative. So number 6 there. And then they will ask you where. So down on the bottom, you're just going to type in the x value. So you type in the number 1 and then hit enter. And then you see the number 2 appears right here. So it gives you the derivative right at that point. So the derivative there is 2. So let me flip back to the 84. So what you do here is you would plot your graph, so plug in your x squared, and then graph it. So here's your equation, you know, exact same one that we just saw with the Inspire. And so for this we are going to hit Secant and then Calc. This is the exact same menu that we showed up when we hit Analyze Graph on the Inspires. And there's our dy by dx. And so you just type in the value. So type in 1, hit enter, and it says dy by dx equals 2. So 4 different ways that we just saw that. Obviously, they all gave us the same answer of 2. If we did the limit definition of a derivative and actually worked out every little detail, you would come up with 2 as well. But we will be working more with the calculators, so you guys will see how that works. So, differentiability implies continuity. This is a very important little theorem that we can talk about. And we talked very briefly about it when we saw an AP problem that told you that a function was differentiable. And I was like, don't worry about it now, but it means it's continuous. So we've got 4 ways that a function could fail to have a derivative, and a discontinuity was one of the examples. So this last sentence is very important. Continuity is an essential condition for the derivative to exist. All right, so if it's not continuous, then it can't possibly be differentiable. So our theorem that we're going to write down here is if f has a derivative at x equals a, then it is continuous at x equals a. So if f has a derivative at x equals a, then it is continuous at x equals a. So I think you guys have probably heard those statements like the converse, like if p then q. I don't know if you've heard if like not q then not p. So if f has a derivative, then it is continuous, which means if f is not continuous, then it doesn't have a derivative, which was one of the 4 issues that we saw in the front. Is the converse true? So the converse means, does continuity apply differentiability? So what that means is if a function is continuous, it's automatically differentiable, and that's not true. We saw multiple examples of that on the front. The best example that we are going to use is the absolute value of x. This is like our classic example here. It's perfectly continuous. There are no breaks, jumps, anything like that, but it's not differentiable at x equals 0. So no, definitely not. The converse is not true. And like I said, the example that should hopefully come to mind first when we talk about this in the future is the absolute value. All right, last little thing for this section, the intermediate value theorem for derivatives. We know the intermediate value theorem for continuity. When we say that a function is continuous, when it goes from f of a to f of b, it must take on every value in between. This is basically the exact same thing, but for derivatives. So we're saying, like, if our function starts with a certain derivative and ends with a certain derivative, the derivative takes on every single value in between. So say, for instance, that we start with a derivative of 0, and then on the end of the interval the derivative is 2, there must be a point where the derivative was 1 if you've got a nice smooth differentiable curve. So let's write this down. If a and b are any 2 points on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. Now, here's the important part. Remember with the intermediate value theorem for normal functions, the function had to be continuous. For derivatives, we have to say that f is differentiable. So if we look at the example up above, that is not differentiable, and it doesn't fit this statement here. This says the derivative must take on every value, between f prime of a and f prime of b. Let's say we had a value of a over here and a value of b over here. F prime of a is -1. The derivative of a is -1, and the derivative at b would be 1. So f prime does not take on every derivative between -1 and +1. For instance, there's no place where the derivative is 0. It's either all -1 or all +1. So this theorem does not apply to non-differentiable functions like the absolute value of x. All right, so that's it for today.